Welcome to this video on more complex electric fields. In the electric field parts 1 through 6 or 7, whichever we've got to at this point, we've been looking at the basic foundation of what the electric field is and then how to figure out the electric field at a specific point in space due to more than one source charge. And so now this video is going to just give you an overview of where we're going and how we're going to incorporate more complex or more advanced electric fields. And this video is specifically calculus-based physics, so AP Physics C. And so if you are looking for something that is just algebra-based, you've gone too far. So if we're looking at a discrete setting, okay, now this means distinct at distinct locations, right? We have been looking at, well, what if I wanted to figure out the electric field at this point over here? Well, we've used the definition of the electric field due to a specific point charge in space, right? And so these source charges, which let's say maybe have the value of positive Q, so let's say they're all the same, they could be different, right? Each one of those contributes to the electric field at that point, right? Due to the distance it is away, the magnitude of the source, and the vacuum permittivity. So all of them individually, I can use this statement to figure out the electric field at that particular point and then do a vector sum. And the vector sum would let me calculate the total electric or the net electric field at that point. Now, this electric field would be different if it was placed here, right? Because now we would need to use maybe this distance, sorry, that's Q, this distance over here, and then this distance over here, but we do the same process over and over again. And we refer to these charges as point charges, not to be confused with test charges because these are source charges, but they're local points in space, right? And so when we're figuring out the value of the electric field, it's due to those specific points. And we refer to this distribution, and you'll hear that word often, as a discrete distribution. Okay, so in other words, the charges are not spread out, they're distinct locations in space that can be dealt with separately, and then a vector sum is done. And usually when we're doing this, we're doing it in some sort of algebraic way. So we're using and employing algebra and vector algebra to add up the parts. But now we're going to move to a point where we have continuous distributions. And continuous distributions rely on concepts of calculus in order to define the electric field. So what do we mean by that? Well, perhaps we have a bar of charge. So we have a metal bar and it's maybe placed right over here. And let's just say, for argument's sake, that the value of this is it has a charge distribution that's uniform. So basically, if I just draw maybe 5 positive signs here, those plus signs represent that it's positive, it's evenly spaced out, but there's not positive charge here and then positive charge here, and it's continuously spread out. So this may be a conductor. Okay, now let's say that I want to figure out what's the electric field at this central point here that's maybe Z units away from the bar. Well, if you think about it, right, the electric field's not just due to this point right here, and we can't treat it like a center of mass or a center of charge if you were using the charge analog, because it's not really the same thing, right? It's saying that basically this end of the bar is affecting the field at that point, and so it is, say, this point right here, and maybe this point right here, and all the points, every little infinite point along this length is contributing to the electric field at this point. So we see that we have this continuous distribution, and so these are often more found in nature in everyday life because objects usually are spread out over a distance. They're not just distinct points. So this doesn't mean that this is not true. It's quite the opposite, actually, because what we use is, if we treat every tiny, tiny little segment of this rod and we call that value dq, right, as a representative of the differential of charge, so a tiny, tiny little sliver of charge, we'd say that that little sliver creates the amount of electric field here, dE, right? And so we can still use this statement as dE equals 1 over 4 pi epsilon naught times dq over r squared. But now what's going to happen is we're going to have to use some sort of integration, right? We're going to use some sort of integration in order to sum up this entire distribution of charges to get the total electric field at that point. So it's really just a continuous version of doing this, what we've been doing before. Now, our goal over the next several videos is to learn a few different methods. Okay, so that's the big picture. So when you're thinking about what the heck am I doing once we get into all these details, you want to think about we're on this side of this spectrum, right? And we're learning different methods. And there's two major categories that we're going to focus on. The one I'm going to call a brute force calculus method, right? This would just be sort of your traditional calculus, integrating, and so on. And then we're going to learn one called, that's oftentimes referred to as Gauss's law. All right, I guess that wouldn't be there. So Gauss's law is actually where we're going to start, because we're going to get some abstract ideas defined. So we're going to start over here with Gauss's law, and then we're going to move to the brute force calculus way, and then look at ways when you pick one method over the other for figuring out the value of the electric field. And so in the next video, the main focus is going to be on a tool that we're going to need to do the method of Gauss's law. And that tool, or that concept, is known as electric flux. And so electric flux is going to be the tool that is used as part of Gauss's law as a method for determining the electric field at a particular point across a charge distribution.